So I'm going to talk about RSA. So I'm not going to prove Fermat's theorem, and I'm not going to do any sort of fancy stuff. It's not my expertise, but I hope you at least you'll be able to understand how to implement RSA and how to attack implementations of RSA. So who here has seen RSA? How do I do this? Actually, I need to finish a poll. Who here has seen RSA in the previous course? Does anybody here see RSA developed before? Know the math behind RSA, the formulas, the proofs? This is really nice that you all know RSA. It's going to make life a little easier for me. So RSA is a crypto system which invented by Rivest Shamir and Edelman, and it lives in a multiplicative group called D star sub n. And this is also called the 7-boom group, because we take the numbers between 1 and what's going on? Okay. We take the numbers between 1 and p times q minus 1, and we throw away all of the numbers which are divisors either of p or of q. So let's take 3 and 5. So p times q is 15. And please prepare to write boom in the chat. And we will write all the numbers. I will going to list all of the members of the group between 1 and 14. And when there is a number which does not appear, you're going to say boom. So the members of Z star sub 15 are 1, 2, boom, because 3 divides 3, 4, boom, 5, right? And then boom, because it's 6, 7, 8, boom, 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 right? 9 and 10, and then 11 is in there. 12 does not appear. 12 is a boom, because 12 divides 3. And then we have 13 and 14, and 15 is not a member of the group because it's 15 is too large. So this group has an operation because it's a multiplicative group. This operation is multiplication. Thank you. You're very excellent boom sayers. So it has an operation. It's called multiplication and modular multiplication, and it's associative. So it means that A times B times C is equal to A times B times C. So the order operation is not necessary. And what does modular multiplication means? It's the A times B modulo n. It's the n. It's the n that's written here. So how much is 2 times 2? Modulo 15. It's 4, right? How much is 4 times 4? It's 1. Exactly, right. How much is 1 times 1? Great. Fine. So we're in a good shape. So the group is closed under the multiplication operation, which means I can multiply whatever values I want, and I will never be able to get out of my group. So if A and B are in the group, then A times B is also in the group. And this is why I threw away all of these boom numbers, because they would get me to 0, and 0 is outside the group. And the group has an identity element. Identity element means that any A times 1 is equal to 1 times A is equal to A. And in our case, what is the identity element? It is exactly 1. Any number multiplied by 1 is equal to 1. And another thing it has, which is at least the weirdest thing in multiplicative groups, is that each element has an inverse. It's r minus 1. And when I multiply r by r minus 1, I get 1. And one of the weird things in multiplicative groups is that numbers can be their own inverses. So, for example, what is the inverse of 4? Yeah, the inverse of 4 is 4, because 4 times 4 is 1. What is the inverse of 2? Right, 2 times 8 is 16, which is actually 1. Fine. So these are groups, and if you want to learn more, there's the Handbook of Applied Cryptography, which has a lot of information. Uh, and I have to talk about a little bit about cyclic groups. If I take an element and multiply it by itself again and again and again and again and again, I don't necessarily cover all the elements in the group. So there are some groups where this happens. In this group, it does not happen. So don't get confused. Yes, there is no generator for this group. In fact, some groups have them. This one does not. Now, because I have multiplication, I can define another operation which is called exponentiation, which just means that 2 times to the power of 3 means 2 times 2 times 2, 3 times. Now, is the group closed under exponentiation? Can I raise a number to another number and run away from the group this way? So the correct answer is no, the group is closed under exponentiation because it's just multiplication over and over again, which means I can't, if multiplication is closed, then multiplying many times is still, then exponentiation is still closed. Oh, yes, so it's closed, fine. Yes, the group is closed. Wow, I was not nice to you. I'm sorry. So everybody was right. You're a great algebraic. You're great mathematicians in cryptography, especially in 17. So here is a question for you, which is not written here. Can I take a number which isn't in the group? For example, 3 is not in the group. Can I raise a number? Can I make exponentiation with a number which is not in the group? Can I calculate, for example, 2 to the power of 3? Is it legal to do 2 to the power of 3? So the answer, which most of you are correct in stating, 2, I can raise to any power I want. This number, I can, thank you, and thank you so much. I can raise, the exponent can be any number, which I can raise to the power of 3, something you can do in the slide. So, now, because exponentiation is closed, if you think about it, I will, if I keep raising a number again and again and again and again and again, I will eventually have to come back to the number once again. And why is that? It's because I'll be running out of numbers. I can't escape the group. I'm closed. So I will eventually find a number. If I raise a number to this number, I will come back to this number again. And this is called the order. So the order is how much do I have to raise the number to get to the number once again. And Fermat's little theorem, which is, it's completely the wrong time to discuss at 7:20 at night, states that this order always divides phi of n, which is p minus 1 times q minus 1. So in our case, this is going to be 3 minus 1 times 5 minus 1, which is 8. Any number in the group, if I raise it by the power of 8, I'm going to get 1. And we can see here, for example, 2. If I take 2 to the power of 2, 3, 4, I get 1. And then 5, 6, 7, 8, I get 2 once again. Okay, so each element has an order, and specifically, if I raise a number to the power of p of phi of n, I get to the number back again. And this is all the algebra that you need to know for the course right now. Now, how does RSA work? And again, there are many ways of doing RSA wrong. I don't want to talk about them right now. But you are going to use RSA. You are going to define, first of all, um, uh, you're going to choose P and Q, which are going to be very large primes, and you're going to multiply them together and get N. N is going to be a very large composite number. Now, it is believed that it's not possible to do factoring in a reasonable amount of time. I can check if a number is prime very quickly, but I can't factor a number very quickly. So if I give my adversary n, it will be very difficult for my adversary to come back and discover p and q. This is according to 2020. It's not NP hard. It is not NP hard. It's not known. There is no lower bound on the difficulty of factoring. It could be NP for all we know, but we don't know how to do it. It's believed that it's very difficult to do factoring. I think specifically it's definitely in NP in the sense that you can check. If I give you the two factors, you can very clearly check if we multiply them and get n. But is it NP hard? I'm not sure. I don't think it's NP hard. So if I get P and Q, it's very easy to go to n. If I get n, it's very difficult to go to P and Q. If I get P and Q, I can get to phi also. Phi is P minus 1 times Q minus 1, and so on. So it's not the same type of problem, indeed. It's not. It's a different kind of problem. Right. So if I want to set up an RSA computation, I'm going to choose P and Q, multiply them, and get n. And I'm going to save a P and Q for myself, and I'm going to give distribute publicly n, and I'm going to distribute publicly an encryption key e. And I'm going to take this e and find a decryption key d such that e times d is equal to 1 modulo phi of n. How do I do this? How do I find this relation? What is the algorithm that I use? Does anybody know? 4 letters starts with X. That's 3 letters. Yeah, so it's extended GCD, or in the cyber world, we call it XGCD. Yeah. XGCD. Okay. Extended greatest, yeah. XG. It's too late for this. XG. It keeps autocorrecting to XKCD, which is the wrong answer. XGCD. Fine, thank you. So extended GCD. You give it. You take. I take E and I take phi of n, and I get in return D. It's very important that E and phi of n be co-prime, but again, I'm not going to talk about it. Let's assume I chose them right. Now, if I want to encrypt the message, I'm going to take the message and raise it to the power of E modulo n. And anybody can do it because n and E are public. And E is typically chosen to be a really small value, so it's also pretty quick to do m to the power of E modulo n. And now I end this operation with the ciphertext C, and now I want to decrypt this. So how do I decrypt? I take the ciphertext and I raise it to the power of D. Now, what does this mean? If C is m to the power of E, then C to the power of D is m to the power of E times D modulo n. But I know that E times D is equal to some multiple of phi of n plus 1. And I know that every number to the power of phi of n is itself. So I get m to the power of 1. Really nice. So now I get m. And you can look at the example. Again, since you all know RSA, A, you all know RSA, and B, it's a really bad time to explain algebra. You can either believe me and go and look about it somewhere else. But why am I talking about this in the middle of the night? What is the implementation of RSA doing all the time, both encryption and decryption? What is the operation that they're doing all the time? This operation is MODEX, modular exponentiations. So to encrypt, you do modular exponentiation, and to decrypt, you do modular exponentiations. And if you want to do an efficient implementation of RSA, you want to do modular exponentiation as quickly as possible. Now, how do you do this? This is going to be something I'm talking about. I'll start talking about it. I'll start talking about it today, and we'll go into more detail next week. But I want to give you some kind of insights on how to do it. So,